Let's look at a practical circuit using this idea of charging and discharging capacitors. And this circuit is called an 555 timer. It's an astable multivibrator. Astable means it's just not stable. It doesn't stay at one state. And multivibrator means it bounces between two different levels. So let's do a little analysis here. The chip starts out, this discharge pin is like an open, and it doesn't allow any current to flow through. Pin 6, the threshold, and pin 2, the trigger, don't let any current flow through them. And this pin 3, the output, is set to low at the beginning, so 0 volts, or basically connected to ground. Now, when we turn on this switch or connect the power, the current is going to flow, and it's going to come to this point, and it's going to see this path, so it's going to flow through this resistor. These are diodes, and diodes only allow current to flow in the direction of the arrow, so it's going to see this diode and know that it can't go through there, so it's going to go this direction because it sees this diode here, and the current's going to flow. It can't flow through pin 7 because it's open. It's going to flow through the diode, and it's going to not flow into pin 6 or 2 because they're pretty much an open, but those are just sensing the potential, and go through the capacitor and back. So the potential is going to rise, and at the point where it hits 2/3 of V1, then the threshold is going to cause the pin 3 to get connected to VCC, or what's at pin 8, and pin 7 is going to get hooked to ground. And now the current is going to start to flow in the opposite direction because the capacitor is going to see the ground. So the current's going to flow. It can't flow through this diode, so it's going to flow up through the other diode, through this resistor R2, and then it's going to see ground through pin 7 and back to discharge. So there's two modes, charging and discharging. So let's take a look at the circuit. Oh, and this potential across the capacitor is going to drop to about 1/3 of V1. So 1/3 and 2/3, those are the important numbers to know. So let's take a look at how we can calculate these values. Okay, so get some space here. So let's look at the charging first. So for charging, we have that we're going to have this V1 minus V1, that's our source for the charge, minus, well, I need to get my initial potential, and that's going to be 1/3 V1. That's when this trigger gets clicked. E to the negative TC over RCC. We'll keep this pretty much general. So RC means our charging resistor, TC means our time to charge. Capacitor is just one capacitor there, so we'll call it C1. And we want that to equal 2/3 V1. We want to know when that happens. So we have V1 minus, we have 1 minus 1/3 is 2/3 V1 E to the negative TC over RC C1 is equal to 2/3 V1. Well, the V1s are going to go away, and I can subtract 1 from both sides, and I get 2/3 E to the negative T over, or TC, sorry, over RC C1, and that's going to, oh, and I need a negative here, and that's going to equal a negative 1/3. So the negatives I can simplify, and I'm going to bring the 2/3 over the other side, so I get E to the negative TC over RC C1 is equal to 1/3 divided by, or times 3/2, and that's just going to be equal to 1/2. Now I'm going to take the natural log of both sides, and if I take it on the left hand side, that's just going to be my value, negative TC over RCC1 is equal to natural log of 1/2, and now I have TC is equal to RCC1 natural log, oh, I forgot my half here, 1/2, and I'm going to use a rule with natural logs that if I have a negative natural log, I just have the natural log of the reciprocal. So it's TC equals RC C1 natural log of 2. So that's my time for charging. Now let's look at for discharging. In this case, I don't have a potential that would be affecting the discharge. So I will have 0 volts minus 0 volts minus, and I'm starting at 2/3 V1 E to the negative T discharge over RD C1, and I want to see how long it takes me to get to 1/3 V1. So I have negative, or actually positive, because I have a negative and a negative, positive 2/3 V1 E to negative time discharge over RD C1 is equal to 1/3 V1. My V1s are going to go away, and I'm going to get and I can bring the 2/3 over to the other side. So I'll get e to the negative t discharge RDC1 is equal to, and I'm going to have 1/3 times 3/2, which equals 1/2. And now I can take the natural log of both sides. And simplify using the negative for the logarithm again. Now notice that my time has nothing to do with my potential, so this operation is independent of the potential that I put across this whole circuit. It's not, I can put whatever potential I want and the timing will not be affected. And I can say that my total period is equal to TC plus TD. The time to charge from 1/3 of the potential to 2/3 of the potential, plus the amount of time to discharge from 2/3 the potential down to 1/3. And my frequency is equal to 1 over TC plus TD. So these circuits are very nice because I can precisely set the circuit for the frequency that I want. And I can change these values of the resistors to get whatever percentage of time on to time off. My duty cycle is what it's called. I can get specific times for my time charge and discharge however I want. Now this circuit is actually pretty useful. I'm going to show you how it works. So you can see how the potential rises to about 2/3. It switches, and then it just keeps going back and forth as a multi-vibrator. Now these circuits are very useful back in the days when intermittent windshield wipers were first or wasn't even heard of. We were making these circuits for intermittent windshield wipers, and what we would do is we would put variable resistors in so that we could change the amount of time that the windshield wiper didn't activate, and then we just had a set resistor for the amount of time that we triggered it, just so that we could have the windshield wiper go just long enough for it to do its cycle, and then we had one resistor that would delay for the intermittent, and we could change that timing period. So this is a very useful circuit. You'll find a lot of uses for it.